All right, welcome everyone. So this is chapter 18 of the Understanding Deep Learning book, Diffusion Models. I think we've got some extra people in this week because this is an interesting topic that a lot of people are interested in. So I'll start by just giving an overview of diffusion. So there's a whole bunch of detail that we could dig into, but I wanted to just kind of start with like here's the process that's happening, and then we can look in more detail as we go through. So the gist of it is that it's an encoder decoder model, but I didn't even personally view it as that from the beginning because the encoder is really just applying noise to the image. So I really only thought of us as training this like image mapping model. And so the encoder, you're just applying noise. You're just saying add noise, add noise, add noise. And then the decoder, you're saying learn how to undo that. So map it back to the original distribution. So when you apply enough noise, eventually the image is just all noise. And so you're trying to figure out how do I undo that and take it from noise back to something that fit in the distribution of the original data set. Um, and people have found that this gives us really, really great generated image. It's been applied in text, it's applied in a bunch of different things now. But I think the real like blockbuster showcase has been images. Everyone has realized that you can get this hyper realistic, very sharp and crisp images. And so that's kind of will be the focus today. There's plenty of other domains that it's applied to, but all of the examples will be image focused. So in the bottom, we can see here's the encoder process. And so you start with some image, and then you apply some noise, you apply some noise, you apply some noise, and you go T steps. And then at that point, it's just white noise. You just don't have any of the initial image anymore. And then in the flip side, you have the decoder that's saying take little tiny steps, undo the noise, undo the noise, undo the noise, until you get back to hopefully roughly the same initial image or an image that matches the distribution at least. So understanding the encoder to start that first part that's adding the noise, the way it's done is you start with your base image and then you say apply one step of noise and then apply another step of noise and then apply another step of noise. And so the equation that this turns into is this over here. So X is our initial input, and then the beta parameter defines how much noise we're applying every single time step. So just kind of plugging in numbers to explore how this works. So imagine if beta was 0, then this would end up being 1. And so we would have X gets a weight of 1 and beta 0 over here. This is our noise over here. So it ended up being just the initial X. We would have no noise added in. If we went to the opposite end of the scale, so instead of 0, we plugged in 1, then we would end up getting 0 for the X and only noise added in. And so this beta parameter, you can understand when you're at different ends of the spectrum, you're adding different amounts of noise every time step. Um, and so we do this multiple steps. So this is how we take our first step. But in the second step, instead of applying it to the initial X, we're applying it to the previous time step that had the noise added onto it. So we can keep going further and further, and we can go from 2 to 100 or 1,000. We can do many, many steps of noise added in. Um, so what this ends up looking like, here's a chart showing the various different input values. So imagine we have three different variables. One of them is over here at maybe -2 or something like that. One of them is closer to 0. One of them is closer to 3 over here. And this chart going from top to bottom is showing as you apply more and more noise, it's eventually going to kind of converge to having a mean of 0 and standard deviation of 1. And so we can see this is how it originally came in. This is just a single variable that we're just applying noise to a bunch of times, and then eventually it gets close to ending up being 0 for all of these that actually started at very different values. And we can see how this moves the distribution. And so we start with these distributions over here, and eventually, after 80 steps, they get smushed to all be kind of more central. Here's another view of this, so we can see the kind of starting distribution over here. We have a sharp peak over here. We have a sharp peak more in the middle, and we can see this represented. This is kind of a similar graphic showing as we go further and further down. Eventually, we have this probability distribution that's centered on 0, and then standard deviation of 1. So even though we started with this pretty sharply peaked distribution where it's many values here, many values here, we eventually get back to just random Gaussian noise with this plot here kind of in the end. Um, so one of the tricks that people have figured out is that with these encoders, if you have to do many steps of noise, that can end up being expensive. So if you're doing 1,000 time steps and you're saying I want to calculate the 970th, it's expensive if you have to say calculate the first, second, third, fourth, all the way through to the end. And so people have figured out some clever tricks and the math to be able to basically say go straight from 0 to 970 and 971, and then you can figure out what's the noise that's applied there. And so that saves you 1,000 steps of calculation of applying noise over and over again. So that's one of the tricks that's very useful to speed up being able to train these kinds of models. So that's the application of the noise, that's the encoder part. And then on the flip side, we have the decoder. And this is a model that is learning to undo that noise. And so the assumption is that we're taking in this random normal distribution, and then we're trying to move it back to the distribution of the data set so that we can generate samples that came from the original distribution. So the hope is then we start with the normal distribution and then we map it back to whatever the data looked like. Um, and so we do this in many steps, so 100 or 1,000 or something like that. And so the decoder can actually be any number of different models. It could be a transformer, it could be a UNet, it could be a CNN. It just depends on what data you're actually looking at. But in practice, because a lot of people are using this for images, it tends to be a UNet. Um, People have just figured out that that's a good model in order to do this sort of mapping for image generation. Um, and so one of the other tricks that people have figured out with the decoders is that you can make it hop step. So if you want to make it go one step at a time, then you have to do that whole expensive process where you say, um, calculate step 1, step 2, step 3, step 4, all the way to 1,000. That means you have to apply your network 1,000 times. And so that can be very slow and compute intensive. And so people have figured out that you can actually kind of short circuit this and say, make it predict the noise for 50 steps or 100 steps or something like that. And that will make it so that you have to do less forward passes in the later steps. So here's an example of what this network might look like. So this is a UNet. We've spent some time looking at this in the past, so I won't kind of dig into the full details. But the one of the interesting things to mention is that this actually has an extra time embedding passed into it. So you have a network that is given an additional input saying that like now you're in mode guess step 100 to 101. You're in mode 200 to 201. So it has an extra piece, so it understands this is the bit that I'm predicting now. And one of the interesting things here is that we're not actually predicting um, the cleaned up image. You're not trying to generate the image with this output here. When you look at that, it's just noise again. So what we're actually predicting is we're saying we have this noised image, predict the noise that was applied to it. So um, the output is just noise back, which might look strange, but what we do with this after is we then subtract it away. So now we have a new image that's the noised image minus one step of noise. Um, and so that's how that works. Um, so how do we train this model? Here's kind of their pseudocode implementation of it. So we assume that we have some training data, the kind of images that we want to generate. We have some model, so that would be some UNet. Um, and then we want to iterate through our whole batch of data across the indexes. And then we want to pull a random time step. So we have, let's say we're trying to do 1,000 steps. We want to pick the 57th or the 600th or something like that. So we're pulling random time steps out of the bunch. And then what we're doing is we're determining the noise to apply given that time step that we're in. Um, and then this loss function, what we're doing is we're basically saying, um, what's the mean squared error of the the noise that the model predicted versus the noise that we actually applied. So we're trying to make it so that the model gets very good at predicting the noise that was applied given a certain step. So what was the noise that was applied um, from 250 to 251 or 500 to 501. So you're trying to teach the model to predict those little steps in between. Um, so I don't know if other people think of it in this way, but the way that I see the diffusion models is it's kind of a hack to get a like extremely deep network. So if we think about the way that the UNet is operating, it's kind of going one step at a time and eating its previous predictions. And so every time um, it's as if it's passing through the same layers over and over again. So if you're doing 1,000 steps, you're passing through those same layers a thousand times, and that's kind of a crazy hack to have this network that would have to be 1,000 times deeper for it to have that same result. And so diffusion is kind of an interesting way of splitting it up into tiny little pieces. And so you can apply this network a bunch of times and get the result of a network that would have to be much, much stronger to get the similar results. Um, so that was training, assuming that we have a trained model now. This is what the sampling would look like. So this is how we actually do the generation of these images. So we have a model, and then we have the noise that we start with. So we just start with some random noise. We pass that to the network, and then what that network is going to do is say, um, given this noise, how do I remove one step of noise from it? And then after that, you just kind of feed that in over and over again, removing more noise, removing more noise. Um, and then eventually, after however many steps you train the model for, 100, 1,000, something like that, then you hope at the end you have a output that is an image that has a distribution that matched your training data, looks like a realistic image. If you wanted it to learn how to generate cats, it knows how to generate cats then. Um, and so um, one of the advantages during the training step um, is that we can actually do this many times for the same images. So the images you can take different noise paths multiple times for the same image, and so given a certain image, you can use it many times with different noise samplings, and then you'll be able to get a lot of different variation on that. And so that's one of the values of the diffusion models is that you end up getting a lot more variety than with something like a GAN. A GAN might get much more similar looking cats versus diffusion, which tends to be much better at getting a wide variety of them. Um, So next section about conditional generation. So like I was mentioning, we train this on a data set, but then one of the difficulties is if we have this data set that just includes tons of images, we don't necessarily want it to just generate any image that is interesting. We might want to guide it in some way. So we might want to say specifically this time generate a cat or this time generate a dog. Um, and so people have figured out various ways in order to guide and steer these models to generate what they specifically want. Um, so in the book, they discussed two different techniques. So one of them is classifier guidance. And what they do with this is at the bottleneck of the UNet, they add a classifier, and then that classifier is trying to guide it to which class the image actually is during the generation. Um, and so on the flip side, you can do classifier free, and then the way that that operates is kind of similar to that time embedding in the UNet, where you're saying now it's an input. So tell the model dog, and then it's going to try to generate conditioned on that. So give it dog, and then it's going to go through all of the steps trying to push it towards dog. In practice, I've seen the classifier free more often, I feel like. Um, that seems to be the more popular approach. Um, yeah, I think that's it for that. So here's some examples of generated images. So on the left, we have these examples. And so what they did is they actually took the text and they passed it through BERT, and then BERT gave out some embedding, and then they passed that to the model. And then the model is able to generate images based on that extra input that it was given. So this is an example of that classifier free approach where they basically said, here, give it some information about what we're trying to generate, and then it's able to do that diffusion process, given the extra embedding to condition on, and you can see that it ends up getting some pretty great looking images. Um, and here's another one. This one is the classifier based one, classifier guidance. And this is with the ImageNet classifier. And this kind of guides the model to the various different classes that were present in ImageNet. So ImageNet has its um, thousand classes. And so you can basically say, push it towards any of those 1,000 classes, and then generate images based on that. Um, I see stuff going by in the chat. Is there anything?
I'm trying to answer some questions, but if anybody still has questions, feel free to unmute and ask.
Yeah, that's all I have in terms of slides. So yeah, if anyone has any questions or anything that they want to discuss,
I have a
perfect
question.
time. Yeah.
On your generated images on the left, it seems like there's so many different combinations of text, right? I mean, if you're limiting it to like a certain number of characters or whatever. So I guess I'm trying to think how this actually works. Do you have to, I guess when you train it, you give it different combinations of words, and then also I guess the corresponding image, and then it learns that.
I think I'd have to look in more detail on this specific example, but what I would imagine is it's probably um, something where they have a bunch of image caption pairs, and then they're able to basically say, take this caption describing the image, pass it through BERT, get an embedding, and then generate a image based on that. So they must have had some data set that had some mapping from text to image to start with. But because the BERT model and some of the other image models are so strong it can probably generate stuff outside of the set that it was specifically trained on.
What's BERT again? Is that the language model?
Yeah.
Yeah, I think that the key thing is, to my knowledge, they're always using a pre-trained embedding from language. So you could hypothetically train from scratch, but to my knowledge, people don't do that. So you're taking advantage of BERT or CLIP or GPT-4, whatever, but something that will give you a a um, a numerical embedding um, based on the text, and that, generally speaking, has been trained on a lot more data than you have, what Ryan was saying, of image caption pairs. So it can be like very high quality, despite the fact that you don't have that many. And so as long as that's generating something very consistent, then you just need enough image caption pairs to, you know, to sort of match up the pictures with the really, really good text embedding. If you were training from scratch, I think you would need a ginormous set of those pairs, which is just not practical.
Okay, thank you.
I have a question regarding the equation, with the square root of 1 plus beta dot product x, that. So I looked at that, and maybe it's just me, but like it seems like that suspiciously kind of looks like log loss or some sort of like probabilistic thing. I was just wondering if there's like an identity there, or if there's like some what the reasoning like is behind the specifically the 1 minus beta and then the beta being connected to, you know, um I'm assuming like the noise with epsilon kind of stuff. Like, do you know anything about like how that's put together, like the identity behind that?
If you want, I could take this one, Ryan.
Sure.
So one of the things with Gaussians is, if you just take an original piece of data and you keep adding random Gaussians from the same distribution to it, okay, eventually the Gaussians will overwhelm your original data, and you'll be left with something that is uh, indiscernibly different from just the Gaussian. Okay. So if you just took like average people's heights and you just kept adding Gaussian noise to it, eventually, well, sorry, people's heights are probably Gaussian, but it's whatever, some distribution that's very wacky, and you just keep adding Gaussian to it, eventually you'll just get something that's, you can't tell the difference between a Gaussian. But if you literally do that, if you just keep adding Gaussian noise, okay, then what's going to happen is your standard deviation, your variance, is going to keep getting bigger and bigger and bigger. Okay, so if I added unit Gaussian noise 1,000 times, then my variance keeps getting bigger. So that's not really what we want, something that just the variance just keeps growing and growing and growing. So what you'd like to do is you'd like to downscale each time you add noise a little bit, so that you keep your variance unit variance. Okay, and if you're familiar, like variance goes with the square, so you need a little square root in there. And if you do the math, what you'll see is that you need the equation that Ryan's shown. Okay. When you have a linear process, what you would normally see, lots of things when they weight stuff, it's just 1 minus beta times the first thing plus beta times the second thing. There's no square roots. That's because you're just doing linear weighting of things. In this case, because what we're trying to do is preserve variance, that's where the square root comes from. So in fact, if you did this without the square roots, it would kind of work, but it would have this tendency for things to go a little bit haywire. But it'd still mathematically kind of work, because you're still adding noise, and it eventually ends up being a Gaussian. However, in this case, instead of you winding up at a Gaussian with a giant variance, if you follow this noise schedule with the right betas, then you will wind up with a Gaussian with unit variance, and it's much more stable, much more predictable.
Right. So beta in this case is sort of like it's like a hyperparameter that controls like the regularization of it. Well, not, I don't know if that's the right term to use there, but like
Yeah, I mean,
how much how much it like overfits, etc. How
uh,
well it learns the variance,
so
kind of.
so there are other places where beta is used for like regularization or whatever. In this case, it's not. This is the noise schedule. So the very, very first diffusion models that people built, there was not this beta 1, beta sub t stuff. It was just, no, just hard coded as 0.1. Okay. And so every step we add 0.1 of noise to whatever the square root of 0.9 is, 0.95 of the image. Okay. And we just repeat that 1,000 times. And eventually, any image you start with, a picture of a cat, you just see snow. It just looks like noise. All right. The miracle is, can you actually train a model to undo that, to reverse that? You know, and so for me, the intuition is that like if you had an image with just a little bit of noise, you're like, yeah, there's like, let's say the cat's eye, like there's the big, black part in the center. And if you just have a red pixel in the middle of that, you're like, that probably came from the noise. So my guess would be that that would be one of the ones we need to undo and make it more black, right? But there's other places where like you may or may not be able to make great guesses. But that's the conditional distribution you're learning in the decoder is like this pixel seems suspicious. I bet this was noise, whereas this pixel seems very reasonable. I bet it wasn't noise. And so you're not necessarily learning that distribution perfectly, but you can imagine there are a lot of clues. So it's pretty easy, at least for me, to imagine how the decoder would learn slightly noisy images, how to denoise them. What's amazing is that it can actually work for extremely noisy images as well. And that was not obvious that it would be able to learn that, right? But the main thing is you do need a noise schedule, and the early ones it was just hard coded. It was not, there's no subscript, it was just beta. Okay. And then they learned because slightly noisy images, it's really much easier for the model to learn how to denoise it. We can actually be more aggressive and use larger betas for clean images. And then when you get towards the end and it's a super noisy image, much harder for the model to learn. Let's actually use smaller. And so that's how, by changing the noise schedule, instead of doing 1,000 steps, then the second generation of diffusion models were able to do 300 steps because they basically took the very early denoising ones and they just did giant ones and they got rid of a lot of steps. But the late ones stayed pretty much the same because you really need to take very small steps because you're very uncertain. So I like Ryan, I liked your analogy of just stacking like 1,000 of these models end to end. And you really can't afford to skip the the super noisy ones. But the super clean ones, it's like you and I, if we looked at a picture of a house with just a little bit of noise, you'd be like, well, that door is all one solid color and there's 3 pixels that are off. I bet those were from noise, you know? And then maybe in the grass, you have a hard time knowing where noise was added, where it wasn't, unless you look really closely. Does that help?
Definitely. Thank you. Yeah.
Yeah. Cool. There was a question in the chat about classifier-free guidance. So I don't know if you want me to take that one too, Ryan.
I'll just say one piece on that. So
Yeah.
the way that I was viewing that, so it's not necessarily on getting better performance, it's on being able to steer the model to do what you want. So if you want it to generate a cat or a dog or a car or something, that's the method that you use in order to do that. So if you trained a model just no classifier free guidance, nothing, just diffusion on all of the data, you're still probably going to get decent images out of it. It's just you won't be able to guide it to the specific class that you want. So if you wanted a cat, you just say, I'm going to generate 1,000 images and hopefully one of them is a cat. And that's probably not the way you want it to operate. And then the other thing I was trying to think of this when I was on this slide, but I couldn't remember it. The difference between those two methods, I think of it as like, are you using the class as an input to the model, or are you using the class as an output to the model? That's kind of the difference between those two approaches. So the classifier free is saying give the model the class, and then through all the layers, it's trying to generate that. And then with the classifier approach, you're saying this is kind of an output of the model, and work at it from the opposite direction.
Yeah. And so what I would add is that early diffusion models, they said, we'll just train this on ImageNet, which has 1,000 classes, and our model will learn how to generate images that look just like what came from ImageNet, but we'll get a random image. So it's like, wouldn't it be nice to be able to pick like which of the 1,000 that you want? You know, I want a plane, or I want a goldfish, or whatever. So so then they had classifier guided ones where you pass in a number between 1 and 1,000. Okay. But you can't really adjust how plane-like the image should be because it's 1,000. Like if you pass in 500, if you pass in half that, you don't get half plane-ish. You get just a completely different class, right? So this notion of how dog-like, how cat-like, how plane-like, you can't do that with just a class. So classifier free guidance says, I will do unconditional generation, and I will do my class conditional generation. And now you have a before and an after. I have random and I have plane. And now if you wanted to say less plane, like you could actually pick a point that's halfway in between. But what people really wanted to do was the opposite. They wanted to say, sometimes when we say the class is plane, I get something and it's not the greatest image. I want to actually bump up. I want to say more plane-like. I want to say make it a plane in all caps. And so then what they would do is they take the difference between these points and they would double it. And so today, when you have your, what do they call it? When you do image generation, God, what is that number that you pass in? That's the what do they call it now? Somebody help me out here. It's you know the strength of your, you know, and if you put in a higher number, you get less variety, but you get more instruction following.
The temperature?
It's not temperatures with language models, but with diffusion models, it's all right, so nobody's helping me out here. But anyway, it'll come to me like 10 minutes from now. But anyway, when you put in that number where the higher number means follow my instructions really closely, but you might get less variety in your images, that's actually the multiplier being used for classifier free guidance. Okay. So if you did like 3, and by the way, they might scale it, so it's not literally the number used, but if you triple the direction, then you are like really super screaming in all caps, plane, make it a plane, make sure it's a plane. I don't want to see anything but a plane. And at some point, if you multiply it by a big enough number, by 5, it'll just break the model and you'll start to get distortions and weird stuff. But that's really the trick, because how else would you sort of take a class and either amplify it or attenuate it? You need to know sort of your starting point and your after. And so the non-class one gives you your starting point and say, oh, you know, oh, if that's the direction I'm moving, then I can actually adjust that. And you could theoretically do things like say, I want 0.5 dog and 0.5 cat, and I want to see what a dog-cat hybrid in this model's ability to generate what that looks like. You might get garbage, and you might get like, oh, well, yeah, I guess that is what a half dog, half cat might look like. So it really gives you a lot of new options to play around with when you use classifier free guidance. Yeah, the guidance scale. Thank you guys. Yes. So the guidance scale, when you're using DALL-E 3 or whatever, um, it doesn't say classifier free guidance, but that's what it is. And that's why they tell you that if you use a bigger number, it'll follow your instructions more closely because it's actually amplifying. But at some point you will get distortion. It's like if you play music, if you turn the amp up too far, at some point the signals get clipped. And if you're going for like a hard rock guitar square waves sound, then you're fine. But if you're trying to get a nice classical music and turn it way up, then the violin's going to get clipped and it's no longer going to sound nice. It's sort of that same concept. If you turn it up too high, your image is just going to get distorted in a slightly different way because the neural network's going to break down. But it's the same general idea. If you're going too far beyond what the system can handle.
There was a question about the loss function. So yeah, I mean, you can use different variations of that. In this, they used mean squared error. So it's basically saying how good are you at predicting the noise, but does that actually tell you how good it is at generation? Not necessarily. You could get a tiny mean squared error, and in theory, you could still end up with generation that doesn't look that great to the human eye. And that number is kind of relative to your specific data set. So you might be great at ImageNet, but that doesn't mean you can generate realistic faces or something like that. So you're limited to whatever your data set is. You can only compare that mean squared error from a single data set. You can't say, well, I got a mean squared error of 0.001 on ImageNet. That doesn't mean the same thing when you're doing it on the celeb faces data set. That could mean something entirely different. So it's kind of difficult to look at a specific number and say if this is a good generation or not. That's one of those things where it's a little bit of an art. You might have to just directly look at the generations and say, is this good or not? But typically what you'll see is that the loss function or the loss value will go down to a certain point and then it just cannot do any better. So you can tell when your model has like fully converged, but whether or not it's going to be good generations or not is kind of has to be manually done probably.
Yeah, and the chapter gets very heavy on the math, but I think it's somewhere around like equations 30 through 39 show the equivalence between predicting the image with a little less noise and predicting the noise itself. And it kind of makes sense because like you can just subtract one from the other and you can convert from one to the other. So uh, but yeah, I remember we were chatting about it. I think it's equation 39 is when they finally show this is the formulation where you just predict the noise. You don't bother with predicting the image itself because of the equivalence. All right, so I'll add another comment. So this is now talking about the original diffusion models. When you use one of the more current ones, there's going to be a couple wrinkles that are added on. So if you use stable diffusion, instead of actually running this process that we've talked about with the pixels, what it's going to do is it's going to encode the image into a much lower dimensional space, right? So your image, if it's whatever, 1,000 by 1,000, it's 1,000,000 pixels of 3 channels, right? It can squeeze it down into a much smaller space, technical term, latent space. So that's the term latent diffusion. Stable diffusion came out with the first latent diffusion model. That's one of the tricks that you see. Another thing is a guy from Stanford, PhD student from Stanford, Yang Song, did some mathematical analysis. And if you're familiar with the what I was saying about like, hey, if you have a house and it's only got a little bit of noise, we can like conditionally say it's pretty likely that that red speck in the middle of the door is noise that was added. I mean, it could be you actually have a red spot on your door, but you're just using, so what is that knowledge or whatever, right? And so basically it's looking at the probability distribution of your data. And in particular, if you look at the gradient of that, or if you look at the gradient of the log of that, that's called the score function. And so if you can learn that, then you can learn, it's quite unlikely to have a big bright red pixel in the middle of your solid colored door, but it's much more likely to have whatever, a bright red pixel in the middle of the lawn or whatever. And so he showed this equivalence between understanding the score function and actually being able to build a decoder that can denoise things. So there's this stochastic differential equation that allows you to model the noise process, and the score function is what you're trying to learn to decode things. He then went on to show that the probability distribution for this stochastic differential equation has an equivalent ordinary differential equation that has the same probability distribution. And ordinary differential equations are much easier to work with. I'm not a super strong ODE guy, but nevertheless, what that means is that we went from 1,000 steps of diffusion to a clever noise schedule that got us down to 300 steps. With the ODE, because it's much smoother and better behaved, you can take even bigger steps. And so then when you convert this from the way we showed, which is the original formulation, to an ODE, now maybe you can get it down to 10 steps. And you'll notice, again, like we talked about, there's this guidance parameter, whatever. Now one of the options you have is you get to choose which mathematical solver you want, which ordinary differential equation solver you want. And you get similar performance, but some slight differences that might help you with one particular image that you're trying to generate. But again, it's that ODE that's doing a multi-step, one big jump instead of little steps. And so that's a vast improvement. And then there's other things even further. Yang Songson has a paper where he tries to actually train a neural net to predict what the ODE solver is going to say. And he got it to the point where he could actually do image generation in one step. Was not that great, was not that high quality, but still pretty freaking amazing that once you've trained a model and you've got all the ODEs and you've got your ODE solver, then you can just use that as training data for another neural network, and it can do a, like a reasonable job that you would say, like, yeah, that's not a high quality image, but it definitely, if you said whatever, an astronaut riding a horse, that is a crummy picture of an astronaut riding a horse. And he showed then that if you repeat, if you noise that a little and then unnoise it, so like in 3 steps. So when you look at the very fastest diffusion models available today, they're generally speaking using these consistency model variations, layers upon layers upon layers based on the original diffusion, which is what we talked about today.
Yeah, one thing I wanted to add with this is you have to get to the level of application. So all of this, you'll learn faster too. If you use stuff like Hugging Face pipelines, so that it's basically go to Hugging Face pipelines, it'll tell you as far as, if this is text to image, select your diffusion models. Also Gemini, so Google Gemini, it uses diffusion. So if you want to see some of the results, just like get it right away. But I highly encourage everybody to get to that point where it's just like, you're running and the changes that you make, you then research, and you'll learn a lot faster that way if it's like in practice.
Thanks for sharing. Yep, there's lots of other tricks that have been used in generation at this point. So I don't even know all the tricks. And then Ryan, you mentioned, yes, people have been applying diffusion now to other domains. I know that AlphaFold 3 uses diffusion. And basically, again, we did this with images. It's kind of easy for you and I just to look and see whether an image is high quality or not. But instead of an image, you could be predicting a housing price, or you could be predicting, like AlphaFold, the 3D position of all of the atoms in a molecule or whatever, you can use it over any kind of data. Yeah, I'm trying to remember. I think Stable Diffusion, whatever it's called, XL Turbo, uses the consistency model. And so that's again where you're training yet another neural network to predict the output from your ODE.
I think I saw that there was just a new stable diffusion model that got released. Maybe I'm
I don't know what the architecture behind it is. And then of course now people are trying to do like 3D image generation and video generation and all sorts of other things. But the foundation is, right, you have some data distribution, you're trying to learn. So, realistic cat images, realistic anything images, realistic audio, realistic molecule atom positions. Whatever that is, you've got your data distribution, which is super complex. You don't understand it well enough, so you're trying to train a neural network to see if it can find the pattern.
I was trying to find stable diffusion release. So they did announce something in the past 5 days. I don't know exactly what, but they're also apparently trying to buddy up with AMD because I think they blew through a lot of their money, and so now they're trying to
Yeah.
find a buyer or something.
Unfortunately, I did hear some stuff in the news. They had a bunch of defections. All right, I think we will end the official part here.